Today we'll read about the heat treatment of steel. So, what do you mean by the heat treatment of steel? We'll go through this. We'll go through the details of this heat treatment and what happens to the steels at different levels of heat treatment. On slowly cooling the steels, the properties of steel are depend mainly on the percentage of carbon. As we know in the iron carbon diagram, the carbon very much affects the properties of the steel. Carbon is very much effective for the properties to deciding the properties of the steel. So different percentage carbon imply different percentage of microstructure, microconstituent and phases. If the carbon constituent changes, then accordingly your the microconstituents and phases will be changed. Though microconstituents and phases are changed, the properties will also be changed. So this is the reason. So pure light and ferrite. Pearlite, ferrite, protected for the high protected steels. These are the these are the regions on which we have concentrated. Then pearlite, cementite, pro-eutected. Cementite means pro-eutected cementite. Okay, for the hyper-eutected steels. There is two regions. So we have already told you that in the last class that we have two regions of the steel. One is the hypo-eutected steel, another is the hyper-eutected steel. Hypo means the region before the eutected reaction, and hyper means the region before the eutected reaction. In that two cases, we are already known that there is the case of there is the microconstituent means the the phases are that present over there is the pure light. Pure light means that is the ferrite and cementite. Again, at the boundary layers, that is pro-eutected ferrite. If you understand that what I am trying to say, this is the case. Okay, this is the case for the hyper eutected steel. See, this is for the hyper eutected steel. Sorry, hypo eutected steel. If there is a hypo, then these boundaries are the what is this? These boundaries are the pro eutected pro-eutected alpha or ferrite. This is pro-eutected ferrite or alpha, and these regions, change the color here, and these regions, the lamellar boundary, lamellar layers are the lamellar boundary, lamellar constituents. These are the these are the what? These are the pure lights. These are the pure lights. Pure lights means the one layer is alpha, then other layer is this layer is this layer is Fe3C cementite. Fe3C. This is the microstructure of what? This is the hypo-eutected steel. The microstructure of hypo-eutected steel. Similarly, if you go to the microstructure of hyper-eutected steel, if you go to the microstructure of hyper-eutected steel, instead of here finding the alpha in the boundary layer, here we will find in the Fe3C. Instead of finding the instead of this pro-eutected alpha, we find here the cementite Fe3C. That's written here. In hyper-eutected steel, we have pure light. I'm just clearing the screen. In hyper-eutected steel, hyper-eutected, we have pure light and pro-eutected ferrite. Similarly, in hyper-eutected steel, we have pure light and pro-eutectic cementite. Thus, this is the in that region, in both the regions, carbon percentage are different. Carbon both different carbon percentage that decides the mostly the properties are changed in these two regions. So how the properties will be changed? So we will go through this in the iron carbon our heat treatment of the steel. So the temperature is high enough, the temperature is high enough and the time at high temperature is long enough for the atoms to diffuse and attain equilibrium conditions. So we are here going for the slow cooling. That means we are for the homogeneous cooling processes, slow cooling. If you are going for the slow cooling processes, here we find temperature is high enough. Temperature is high enough means that we have the temperatures at the eutected reaction. What is the temperature? That is 727 degrees centigrade. 727 degrees is sufficiently high. And for eutected enough time and enough temperature. Time and temperature both are sufficient for the atom to diffuse and attain equilibrium conditions. Both the time and temperature is sufficient here. That the atoms will diffuse and attain equilibrium conditions. This is the case. Then you see here the part of the iron carbon diagram. This is the part of the iron carbon. This part is which part? This is the eutectic reaction part. See, this is the eutectic reaction part. This is the region where eutectic reaction is eutectic reaction takes place. This is the region. In this diagram, I am showing the zooming portion of the eutectic reaction phase, only the eutectic reaction phases. So at that point, what is the carbon percentage? 0.8 or somewhere 0.76 will be written here. So this to the right of this diagram, to the right of this diagram, what is that? To the right of this diagram, this is hyper-eutected, and to the left, that is hypo-eutected reaction. So, in both the cases, we have the pure light and pro. This is the if you go to the left side, we have pure light and pro-eutected ferrite. If you go to this side, here we have pure light plus pro-eutectic cementite. This is the region. If you see what is the carbon percentages over here, see this. There are two regions generally shown to you at the hypoeutected steel compositions. They is 20% perlite. If you see this is 20% perlite. If you going on increasing from this side, from left to right, the perlite percentage will be going on increasing as the carbon percentage increases here. So as the carbon percentage increases, both the perlite also increases. So this is at the low carbon steel. We have generally 20% of perlite. We have generally 20% of perlite. When we will move to the medium carbon steel, that we have the percentage of generally 70% of perlite. Okay, so what is low carbon steel is within 0.2 up to 0.8, that we are saying that is a medium carbon steel. So that is medium carbon steel has the generally of 70% perlite, and the low carbon steel, that is we have 20% of perlite micro constituents. So this is the diagram. This is the part of the iron carbon diagram. This is the eutected part of the eutected iron carbon diagram, eutected reaction of the iron carbon diagram. If we see the what is the happens to the what is the effect of the different phases on the properties of the materials. If you see there, this is the hardness, tensile strength, and your elongation. Hardness, tensile strength, and elongation with increase in percentage. With increase this is the elongation. This green line is for elongation. With increase in weight percentage of carbon, the elongation means ductility decreases. If the carbon constituent increases, the ductility decreases. The ductility decreases. If the white line is tensile strength, with the increase in weight percentage up to certain level, that the tensile strength increases. That is up to zero point 0.9. That is in between that 0.9, in between zero point 0.8 to 9, that is the tensile strength increases. Then after that, the tensile strength will be going on decreasing. Okay. And if you see the hardness level is continuously increasing with increase in carbon percentage. So this is the effect of carbon on the properties of the material. If you see this diagram, okay. So this diagram will clearly show you the elongation decreases, the tensile strength decreases up to the 0.9% of the carbon. Then after that, it will be started decreasing, but the hardness will be going on increasing. Hardness always increases with the increasing carbon percentage. So this is also the properties, also the impact energy, tensile strength. The tensile strength increases up to, see here, this is of maximum 0.1 for the composition of carbon is given here. So tensile strength increases, Brinell hardness increases, also yield strength also increases. Strength and hardness generally increases in the perlite and ferrite regions. If you're going to the perlite with increasing percentage of perlite, then with increasing in carbon percentage also, the tensile strength started to decreasing after 1% of carbon. So here the impact energy, if you see the impact energy, that impact energy will decreases here. The reduct area will decreases here, and the elongation means ductility is also decreases with increasing in carbon percentage. So you can understand what happens to increase in carbon percentage to the properties of the steel. That impact energy decreases, area decreases, and the ductility of the material decreases. Whereas the tensile strength, hardness, and yield strength will increases. See, this is the better diagram to show you the what is the effect of the grain structures also. There are the different grains with the percentage of carbon. This is the grain structure. Different grain structures are given here. As we have discussed, that tensile strength increases, renal hardness increases, and impact energy decreases. And ductility decreases. Ductility decreases, impact energy decreases, and the hardness and the strength increases. So this is the at different levels. This is the with increase in carbon percentage. This is the microstructure up to 0.2. This is the microstructure of the carbon. This is the different microstructure levels. And if you increasing in above 1% of the carbon, we have a equiaxial grains. That is called as equiaxial grains. Okay. So this is all about the properties, and then high heat treatment. If the question arises here, high heat treatment. What do you mean by heat treatment? Heat treatment is nothing a heating and cooling process. Heat treatment means a heating and cooling process. Heat treatment does not mean the only heating. Heat treatment, a heating and heat process, it consists of heating and cooling process. For which, why we are going for the heat treatment? To manipulate structural changes. Why we choose heat treatment? Heat treatment is nothing a heating and cooling process to manipulate or to engineer proper structural changes. So affect the materials properties. If you need some properties, if you need high strength, then we will have to we'll have to go for different properties, different processes of heat treatment. If you go for the decreasing the tensile strength, decreasing increasing the ductility, then we have to different processes. So these can be achieved by the heat treatment processes. So heat treatment is what? Now, by varying the manner in which plain carbon are heated and cooled. Plain carbon steel. That is not cast iron. I am not talking about the cast iron. I am talking about the plain carbon steel. The manner in which plain carbon steels are heated and cooled, different combinations of mechanical properties of steels can be obtained. So main aim is to attain different mechanical properties, different combinations of mechanical properties. So that's why we are going for the heat treatment. Heat treatment means the heating. It is a heating and cooling process. It is a process. It is not any method. It is a process. The resulting mechanical properties are due to changes in the microstructure. Mechanical properties, how will achieve the mechanical properties? By changing the microstructures. So properties can be tailored by changing microstructure. So that means here we conclude that if the microstructure changes, then the properties of the material changes. That's all. So we are going to then we are going for the changing the microstructure. The microstructures are changed by the heat treatment process. If the during the heat treatment process microstructure changes, then we will have some different properties of materials. So the development of the microstructure is not instantaneously, and it is ruled by the diffusion of atoms. How the microstructure will develop? The developed will in the microstructure will be developed by the diffusion of atoms. Diffusion of atoms is not an instantaneous process. It will be a process, certain time period of process. So the change in microstructure will be attained by the diffusion of atoms. If there is a change in microstructure, then there will be the different mechanical properties will be achieved. So that will be done by the heat treatment process. So heat treatment process that's why it is called as a heat treatment process. So see this is the diagram. The structural effect of heating a steel casting continuously that is the plain carbon steel. That means 0.35 percentage of carbon to a temperature just above its upper critical, followed by cooling at room temperature. This is the processes here is given to you. First, we have 0.35% carbon is given to us. So we have the austenite microstructure. This is the grain structure, microstructure of that particular case. When we are heating at we are going to heating at a upper critical temperature. This is the temperature level, the temperature level. So then we have after the during the cooling process, what we obtain in mutated reaction, austenite is converted to first austenite plus ferrite, gamma plus alpha. This is the pure gamma. This is the pure gamma region. This is the pure gamma region. This is alpha plus gamma region. This is alpha plus gamma region. Then we have ferrite and pearlite. This is the alpha plus Fe3C region, cementite. Here that is called as the pearlite region. So upon heating here, so what happens here? See that coarse. What is the microstructure? What is the microstructure? The coarse plates of ferrite and are deposited on boundary layer. This is the boundary layer. See, this is the boundary layer. This white light. I am just changing my. Mhm. See this regions. This white regions are the boundary layers. So in boundary layers, the coarse pearlites are deposited. Sorry, coarse ferrite is deposited. This is the boundary layers. In austenite, there is the coarse ferrite is deposited. So again, we have the pearlite microstructure. In pearlite microstructure, completely there is the in boundary layers there is the ferrite is deposited. The boundary layer is the ferrite boundary layer, that is called as pro-eutected ferrite, and others are the lamellar microstructure. Lamellar microstructure. Pearlite is in between that there is a pearlite. Pearlite is lamellar microstructure. Pearlite means alpha plus cementite. Upon hitting that, we are hitting it. See, this is we are now hitting it. Upon hitting it, see, this is there is the coarse. These grains are very coarse grains. So if we hit that, fine austenite absorbs the coarse ferrite. Here, what the austenite levels or austenites present over here, that will absorb all the coarse ferrite. What the coarse ferrite are here, they will absorb it. See the change in microstructure from this figure to from this figure. See the microstructures. The change in microstructure. See this from this to this. How the coarse structure will be a fine microstructure. Then again we are heating it. So again we during the heating process, a fine grain austenite will be formed here. A fine grain austenite. This is the fine grain austenite. Fine. Here it is coarse. This is coarse grain. This is coarse grain austenite, but here we find the fine grain austenite. Then after that, we are going to the cooling process. This is the heating process. Heating is done at upper. This is the upper critical temperature. Heating is done at upper critical temperature. After that, we will go for the cooling processes. If you cool down that, again the microstructure will be modified. See this. See the diagram from this to this. How the microstructure will be modified. Grains will be growth. The grains will be recrystallized. Recrystallized grains will be formed here. Okay. So after that, fine the last microstructure you will see here. It is a fine grain ferrite and pearlite. We find here a fine grain ferrite and pearlite. If there is the grains are fine microstructure, it will provide us the better mechanical properties. So this is how the heating process, the heat treatment process will be taken place. Then we'll move to the next slide. There will be another term, isothermal transformation. Remember these things. The isothermal transformation. This is going to be very important for you. Here, you'll start entering into the TTT curve, that is called as time temperature transformation curve. So it starts with the isothermal transformation. Considering in that last case, we are talking about the slow cooling processes. We are talking about the slow cooling processes. If consider a rapid cooling from A to T1 in the diagram for the eutector steel. So you see here, just making it small. Huh. Is it visible though? Is it
Yes,
visible?
sir. Yes, sir.
Yes, sir.
So see here, consider rapid cooling from A to T1 in the diagram of an eutected steel and keeping the steel at this temperature for the eutected reaction to occur. Rapid cooling. So here is the A and T1. See this. This is A and this is T1. Can you find that points? I'm showing here to you. This
Yes,
is
sir.
A and T1 points. So that we are going for A to T1, we are going for the rapid cooling process, not the slow cooling processes. That is the which type of reaction is that? Here the upper part is solid, below part is the alpha plus gamma. Upper is the alpha, upper part is the austenite, solid austenite, and below is the alpha plus cementite. So which type of reaction is going on here? That is completely eutectic reaction. So in eutectic reaction, that will be from A to T1. If you are coming by rapid cooling processes in T1, will reach at the eutectic reaction to occur. And eutectic reaction occurs means eutectic reaction. This line is called what? Which type of line? This line is called as your isotherm line. This line is called your isotherm. I am using this isotherm very much in frequently. Isotherm line. This line is called as a isotherm line. These lines in isotherm means at constant temperature transformation occurs. At constant temperature, the transformation occurs. Then which transformation will occur? That gamma will be converted. Here the gamma will be converted to alpha plus cementite Fe3C. That's it. Gamma will be converted to Fe3, Fe3C. Pure light. Gamma will converted to Fe3C. So what is the gamma? In gamma, what is the percentage of weight percentage of carbon? That weight percentage of carbon is generally we are talking somewhere we are taking 0.8, 0.76 or 0.78. So here it is written as 0.78. See this reaction. Gamma will be converted to alpha. Gamma has here the gamma has the carbon percentage of what? Now 0.8 percentage of carbon. That is somewhere it will be written as 0.78. Some books it will be written as 0.76. So it will be in between 0.76 to 8. That is all right. So 0.78 weight percentage of carbon, that will give us alpha. In alpha, that is the what is the weight percentage of carbon? What is the ferrite as the maximum weight percentage of carbon? That is 0.02 percentage of carbon. That is 0.02. Okay, in cementite we have 6.61 percentage. Have you understand this reaction or not? We are already discussed these reactions previously. So this is the austenite on time will transfer to ferrite and cementite. Here also, when you are moving from A to T1 rapidly, but austenite on time will transfer to ferrite and cementite. Carbon diffuses away from ferrite to cementite. Carbon will diffuses to ferrite to cementite. Then temperature affects the diffusion of carbon. Here, the temperature will affect the diffusion of carbon. If you see here. At temperature T1, the transformation will occur gradually. At temperature T1, if you are talking about the temperature T1 only, that is the at temperature T1, there is isotherm temperature transformation will occur gradually, which following a S-shape curve. If you go for a, if we are going for a fraction of transformation y small y to the logarithmic of heat treatment, small y to the logarithmic of heat treatment time a log t time. This is the log t time, and this is the fraction of transformation y small y. If you draw there, you will find a S type of curve at isotherm. At temperature T1, the transformation will occur gradually. The transformation will start gradually. Okay, this is the started from here, from this point. The transformation will started from this point, and it will be following a S-shape curve, this type of curve. This is followed by this equation. That the curves will followed by this equation. That equation is called as your Abraham's equation. Hmm. That curve is followed by this equation. Already mark is there. That curve is followed by this equation, that called Abraham equation. Y is equal to r minus exponential minus k to the power n. Y is the fraction of transformation. T is the time for the transformations. So let's see. What is that Abraham's relationship? Abraham's relationship describes the fraction of transformation that occurs as a function of time. That Abraham's relationship describes fraction of transformation that occurs as a function of time. This describes most solid-state transformations that involve diffusion. Thus, mechanistic transformations are described. So that is there is not mechanistic transformation. I'll told you what is that mechanistic transformation during the TTT call. So this describes most solid state transformation that involve diffusion. Okay, so see that the direct diagrams here. Here, what happens here? We have the alpha, then the layer of cementite, ferrite, and cementite. This line, these pink type lines will be the ferrite, and this gray lines are the cementite. Ferrite is alpha, cementite is Fe3C. See, this is Fe3C, and we have before that what we have the austenite that will be transformed, that will be transformed. So this is the carbon diffusion, increasing in carbon percentage, the carbon diffusion process. In the carbon diffusion process, we will find the cementite and the growth direction of light. So this type of lamellar microstructure is called fuel light. So this arrow shows us the good direction of fuel light. Fuel light, how the fuel light is formed by the Abrahamic relationships. So Abraham relationship is nothing but describe the fraction of transformation that occurs as a function of time. That occurs as a function of time. So if you see that the relationship fraction of transformation, the R is equal to R means the rate of transformation. The R is the rate of transformation. That R equals to 1 by root over T. Okay, 1 by root over T, the rate of transformation. But it can also be given by R is equal to AE minus Q by RT. We are already aware of this equation in vacancy. Okay, the rate of transformation. So the fractional transformation will be like that. This is the time. This will be the time, and this is the fraction. Though don't disturb me during the classes. So mute you all. So this is the rate of how the transformation occurs. How the transformation occurs. Okay. The S-type curve. This is the S-type curve. The transformation occurs. Similarly, if we see there is a series of S-type curves, will be transformation occurs like in S-type manner with different temperatures at different temperature levels. At different temperature levels. Okay. So this is equilibrium transformation temperature, and this is see equilibrium transformation temperature. How the transformation will increases. This is the temperature, and this is the growth rate, and this is the temperature versus time. The temperature versus time. So see this diagram. This will be going to be very important for us. This is the this diagram, different diagrams with temperature versus rate. Temperature versus this total line. As this dotted line shows the growth rate. Second, this dotted line, the nucleation rate. Nucleation means the grains have nucleated after the recirculation process, after the heat treatment process. So this is the nucleation rate diagram. The nucleation increases with the decrease in temperature and rate, with increasing rate of transformation. With increasing rate of transformation and with decreasing temperature, the nucleation rate increases. But the growth rate increases with increasing transformation and increasing rate of increasing temperature. So these types of curve will be formed at the total rate of transformation. This type of curve, the solid line. This type of curve will obtained during the total rate of transformation. That is oscillatory transformation to pure light. So again, this is the temperature versus time graph. If you see this type of C type of curve, the time for 50% transformation, this type of curve will be formed. This type of curve will be very important. From this, we will be go for the isothermal transformation. Uh, the rate of phase transformation is the product of the growth rate and nucleation rate. The rate of phase transformation. The rate of phase transformation is the product of the growth rate and the nucleation rate. This is the rate of transformation. This is the rate of transformation. This rate of transformation is the product of the growth rate and nucleation rate. This both the products show this diagram. This two dotted lines product will give us this solid line. Okay. Then giving the maximum transformation rate at critical temperature. At critical temperature, the maximum transformation will happen. So, consequently there is a minimum time T minimum that is given to us. This is the T minimum for the maximum transformation required for the transformation given by the C curve. Okay, this is all about these two curves, and which here we will go to the iron carbon equilibrium diagram. Just a minute, I have a call. I have to attend that.